Hi-oh, here we are again. Satellite motion. We're going to bring together the idea of energy and gravity and what keeps those things up in the sky. Well, the simple orbit to talk about is a circular orbit. Now, let me just say that there really is no such thing as purely circular. But if there was, this is what it might look like, as you can see from the picture to the right. On the left, I have a few ideas, and we're going to relate this to the picture on the right. So velocity, well, what do we know? When we talk about energies, velocity is due to the kinetic energy of an object. It can be directly related. And of course, the kinetic energy relates directly to the potential energy. It's probably easiest to start by talking about potential energy, which is height determined. The height of our satellite at all the locations is the same. It's still accelerating by gravity the same. It still has the same mass. So what can we say about the potential energy? Well, it's the same everywhere. Okay. So if that's the same everywhere, what can you say about the kinetic energy? It must be the same everywhere as well, because the total energy is potential plus kinetic energy. This hasn't changed, which means that hasn't changed. So this is the same everywhere. Since velocity is related to the kinetic energy, we know if the kinetic energy stays the same, the velocity must stay the same. This satellite is orbiting at the same speed everywhere in its orbit. Now what happens if we move our satellite to a higher orbit? Well, the potential energy increases, therefore the kinetic energy decreases. And in doing so, if the kinetic energy decreases, that velocity must decrease as well. Now, can you apply this to an elliptical orbit? This is actually what happens. We know the total energy has to stay the same. We know over here at C, there's a lot of, the distance is very, very big, therefore it's a lot of potential energy, and the kinetic energy is very small. Over at A, it's a little bit of potential energy, but a lot of kinetic energy. So what's that tell you? Well, it tells you the velocity at A, the object is moving very quickly compared to the velocity at C. B and D are just distractors, although we can see we're getting farther away up here at D compared to B. So D is not moving quite as fast as B. And same thing. So as we move to a higher orbit, the object gets slower. The potential energy is less. Well, this elliptical orbit, it turns out, Johannes Kepler, we're looking at, about 1600, he actually took the data from a guy named Tycho Brahe and did something with it. He actually looked at Mars. And he realized, contrary to what was believed, the orbits were not circular. They were those elliptical orbits. And he came up with 3 laws based on that. And you could, of course, demonstrate this yourself. Put 2 pins in a board and put a string around them, and you could trace out a nice elliptical orbit. Those pins would be the foci. So he said, well, it turns out the sun is at 1 foci, and the orbit of the planet is an ellipse. His second law said, remember, we're going slower over here, said if you draw an imaginary line from the sun to the planet, it sweeps out an equal area, so there's this area here, in equal time intervals. So it takes the same amount of time to make that area as it does this. These areas happen to be equal, and the time to do it is the same. And of course, his third law and final law gave us this nice formula, which was t squared equals ka cubed. To put it simply, k is a constant as long as you keep things in astronomical units as a distance and years as a time. A would be the semi-major axis, in other words the distance, and the time would be, or t would be time. Things work out relatively nice. You can figure out when the period, or what the period of that planet is. There you go.